In this video, we're going to review some of the work we did previously with binomial probabilities, and I'm also then going to go a little bit further and talk about some of these properties of the distribution. Okay? Airlines claim that 95% of flights are on time. In a random sample of 20 flights, what's the probability that none will be on time? And you can see here my reminder of how we show our work for problems like this. So none will be on time. So it's a binomial distribution. 20 is the size of our sample. Probability is 0.95, and we are interested in 0. Okay, so I have typed this in. I'm not going to necessarily type all of these in today because I did that in a previous video, but I did want to just remind you. We go to the distribution part of our calculator. That's second vars, and we go down to binomial PDF. PDF is because we're looking for one specific probability, just the probability of 0. And then we do the size, probability, and the number of interest, which was 0. And you can see a very, very small number here, or 9.5 times 10 to the negative 27th. And it should be. We obviously should have flights on time. Okay? What's the probability that all will be on time? So now, all that's really going to change is we're going to change this setting to be binomial 20.95 and all 20. So we would just simply change that 0 to be a 20. We get 0.358. And then what's the probability 12 will be on time? So binomial 20.95 and 12. So again, we would just change that, what I've circled there to be 12. It's another small number if you're kind of following along and maybe checking. It's 2.66. I guess I could just say 2.7 times 10 to the negative 6. And again, the reason it's so small is because we should have more flights on time. At least one will be on time. Remember, at least one, we use complements. We do 1 minus the probability of none, which we calculated, of course, our first thing. Now, in your calculator, it's going to do a round off. I'm going to put a little approximation. It's going to say that's essentially 1 because it's 0.999. It's 27 nines. Okay? More than 18. For this one, I would use the, you have a couple of choices. You could use binom PDF, figure out the probability of 19, the probability of 20, and add those together. Or we could use complements. We could do 1 minus binomial setting 20.95, and we could do the x is less than or equal to 18, and we could use the CDF function on our calculator. So here I've done that. You can see CDF. So that's a cumulative distribution function. So this takes all the probabilities from 0 up to the number you put here, 18, and adds them all together. So it's actually a very high probability that either 19 or 20 flights will be on time. And finally, in this sample, how many flights would you expect? Well, if 90% are on time, you'd expect that 19 would be on time. Okay, this is our expected value for this distribution. So along these lines, we have this formula now for expected value for binomial, which is the size times probability, what we just did, right? That 20 multiplied by 0.95. Okay, so how we'd interpret this expected value. If many samples of 20 flights were taken, we would expect an average of 19 on-time flights. Okay? So kind of look that over, get that wording down in your head. Now the standard deviation formula, you see up here, n times p times 1 minus p, and then the square root. So for us, it would be the square root of 20 times 0.95 times, of course, 0.05. I'll write it by the formula, but like that. And I'm going to show you really quickly the proof for that in just a moment. But let's, again, so this was 0.97. Let's talk about interpreting this. If many samples of 20 flights were taken, we would expect individual flights to vary from the mean by, or individual samples, excuse me, to vary from the mean by 0.97 flights. So if we took a bunch of samples of 20, let's kind of round that 0.97 just to 1, because of course we'd like to talk about whole flights. If we took a lot of samples of 20 flights, we went to multiple airports and took a sample of 20, we would expect those individual samples to be within one flight of that 19 expected. You know, we'd say, well, we wouldn't be surprised at anything between 18 and 20. The nice thing about this is it kind of ties the binomial distribution back to the normal curve, and a lot of times they will have a similar shape. Now, of course, this distribution being centered around 19 flights out of 20, it's going to be very skewed to the left. But again, we can maybe make some links here between these two things. So these two formulas are definitely things to know. And these interpretations, right? That if you took many samples of 20, you'd get about 19 on time. If you took many samples of 20, you wouldn't be surprised if those samples varied by, in this case, about one flight in either direction. Let's look at the proof. So I just set up a very simple distribution of just kind of success or failure, and you could certainly change these random variables to be different things, but I wanted to just show you the kind of basic calculation here. So, of course, expected value is random variable times probability plus random variable times probability. 0 times anything, so it's just p. So this is the expected value of doing it once. If you did it n times, then of course you simply multiply your expected value by n, and you get np. So now the variance. Remember, variance is probability times random variable minus expected value. Remember, our expected value is p squared. So you see that I did that here too. 0 minus p is negative p, but negative p squared is just p squared. So that's my simplifying. Then I noticed that each term here had a p and a 1 minus p, so I factored it out. It left me with a p from this first distribution and a 1 minus p from the second part. That's 1. So I have this. And then I said, well, I don't just want to run it once. I want to run it n times. Like our earlier flight example, it was 20 flights. Well, then I would have to add up 20 variances, or n variances. So you add n of these up, and then you square root to get back to standard deviation. So again, those are just the quick proofs of these formulas.